Hey, welcome back, everyone. Today, we want to continue our discussion on malware and system security, a little bit of the hardware security. And so a little bit of recap, a quick recap, just to make sure that you double check and make sure you already understand these terms and it doesn't look like completely new to you. Things like code reuse attacks, return to libc, control flow integrity. We'll talk more about CFI next on Thursday. Next Thursday, yes. Gadgets, just small instruction sequences, address-based layout randomization, and so a lot of protection. And last time we talked about metamorphic virus. So viruses, they just keep changing and they use encryption. And we also, today I want to say a little bit more about dynamic and static analysis. Last time we said if you have those kind of encrypted virus, you want to run them because just by looking at the binary, they may look just very random. They use encryption. The simplest is XOR a key. And so that when after if you don't know the key, then it's just a complete random bit. Dynamic analysis means you have to run the code. Static analysis means you look at the binary or source code. If you have the source code, most of the time you don't have the source code. Dynamic analysis is beneficial. The advantage is that it can handle obfuscation, reflection, like the dynamic feature. This huge pile of mess is a code snippet from a malware, a mail app called Fake Inst. It uses a lot of Java reflection. Java reflection is where you don't know the class name, you don't know the methods in the class, you don't know the fields of the methods, and then you are like, okay, get the method of this object. Or you say, please tell me what are the fields associated with this object, this instance. And so that information will really depend on the actual object being passed into this get method call for name, get field. And statically, you don't know what information gets passed. And so the nice thing about dynamic code analysis is that you will be able to know it because you're going to run the code. However, it comes with a price. You have to actually get the code running. That means you have to have the actual, for app, you have to have the Android environment or iOS. For mobile apps, it's relatively simpler because relatively simpler, but then its version has to still match, right? So, but the IoT, the Internet of Things, is a lot harder. Even if you have the code, it depends on the actual embedded system. Is it ARM? What version of the architect, the operating system, the library, and sometimes if they use an old library, you have to then find out the archives, the version, to make sure things match. They don't necessarily backward compatible or forward compatible, and so get things running sometimes could be difficult. And another challenge which I show here is that you do have to trigger the interesting behaviors. Things may be running, but then maybe just idling and just waiting to take user input. If you don't give any inputs, the program won't do anything interesting. For apps, it's very user-centric. You have to trigger apps to start doing things. You have to click, and so that takes time. This is a figure from a paper that one of my former postdoc led on a dynamic analysis work for Android apps. And the idea is still malware classification. You want to identify whether some Android app is benign or malicious. And to do that, you have some training data. And training data usually means you know the label, good or bad, and either someone have done it or someone manually confirmed it. And your task is to make sure that you want to come up with some algorithm, some model that can tell unknown apps, new apps, And in this particular case, it's dynamic analysis. You collect traces. The traces usually means, you know, the logs, you know, system call logs, the API call permission logs. And so, you know, for that, you have to get the app running. And you see here, this is the interesting word, instrumentation. And this is just a fancy word for modifying the code. And so you don't necessarily run the original app. You want to log more information, and you want to tell the app to spit some information as it's running. So you have to change the code. And most of the time you don't have the source code because the app developers or the malware writers would not give you the source code. And so you analyze at the binary level. But luckily for Android, there are so many tools, and Google has many tools. And one of them is APK tool, can do some sort of reverse engineering and make it happen. So this is, I wanted it's just to talk a little bit more about Android app classification, because we, at least the research community has moving a whole lot to the Android apps in terms of malware identification. You know, before, like 2 decades ago, there's Windows malware and so on, but then it's a lot of them are in the mobile form. And so one of the idea for the class project is to do some sort of Android app analysis for security, you know, malware detection. And I encourage you to do dynamic analysis. And there's this tool called Monkey from Google that allow you to trigger UI components on its own automatically. So there are a lot of tools, and then you can download some apps from Apple Play Market and just play with it. Last time we talked about VirusTotal. That is another way to analyze the Android apps. And then VirusTotal, you really do it statically, I believe, like without running, just to look at the bytecode. So malicious code has been around for a long time. We've been talking about Fred Cohen's article on computer virus multiple times. And this is, here, let me see, let's orient ourselves. This is, who is this? Dennis Ritchie, one of the Turing awardee in 1983. He received the Turing Award with Ken Thompson, who is here, and both of them received the National Medal of Technology from Bill Clinton. And both of them were attributed to inventing Unix and the C programming language. And also, I think they also invented the B programming language, a predecessor of C. And they, during a speech, Ken Thompson reflected on reflected on trusting trust. And this is around 1984. So then how many years ago? Almost 40 years ago, okay? A long time ago. And so Ken Thompson said, the press must learn that misguided use of a computer is no more amazing than drunk driving of an automobile. And he also mentioned Trojan horse. And so this is a very mild statement about cyber attacks, right? So nowadays, 40 years later, of course, we know cyber attacks can be extremely powerful and dangerous and evil. You know, millions of pieces of personal information get leaked. Last time we talked about shutting down steel mills and causing fatalities. But then 40 years ago, people think, oh, defacing websites, how bad could that be, right? So a lot of things have changed. This is very interesting. I'd like to share with you. Feel free to check them out. Those are real-time maps of internet attacks. It's unclear how real-time are they, but then you see the attacks just happening all the time. And a lot of time that it's because that there's so many scripts that make this automatic. and so it's really not very high tech. And of course, a lot of the basic attacks can be prevented if you know the possible attack patterns. And so, but then it's just very, very common. I have someone mentioned that, you know, University of Illinois hosts one of the supercomputing facilities before, and then they just routinely get DOS attacks and those kind of attacks all the time, and then you know, so it's, you have to be very quick in terms of installing the security protections of a workstation. If you have a new computer, you want to plug it in, you know, connect it to the network, and then maybe download antivirus software and to protect it. But then, you know, there's a short window you may not be protected. You could be in bad shape, and so because there are just always people who try to access, attempt to access it. And Trojan horse was mentioned by Ken Thompson back in the 80s. So what is Trojan horse? I just want to make sure that this is some language that you're familiar with. It's just a type of malware, and it could be an app. Like an app could be a Trojan horse, meaning that it's just to disguise itself as something useful. It could be a screensaver app, ebook app, weather app, but then once you install it, it starts to steal your information and access a premium phone numbers and so on, you know, leak your information. And so it's misleading. And of course, it came from the ancient Greek story tale of a Trojan War in this town called Troy. And so the city of Troy has apparently a big gate, and then the residents, one day when they open the gate, and then during this Trojan War, they find this big wooden horse, and they were like, oh, this looks really nice. So, thank whoever come up with this gift, and then they drag them back into the city of Troy, and then all of a sudden the wooden horse opened up, and there's a whole bunch of Greek soldiers rushing out and take over the Troy city. So it's really bad for the Troy people, and make sure that you don't get fooled into downloading Trojan horse. Kevin Mitnick is the face of social engineering attacks, and he wrote a whole bunch of books, and I think with some helper writers, like shadow writers. But one of the book, and he was describing a bank hack, but then the bank has installed some sort of a pin to make sure only authorized employee with a PIN can complete certain transaction. And so he was pretending to be the boss of someone, a bank employee, to trick that employee into telling him the PIN in order to authenticate the employee. And then the employee end up giving away the PIN to this stranger over the phone in order to convince the stranger that the employee himself is authentic. And so he is actually, Kevin Mitnick is not very good at technical work. So it just shows how dangerous this social engineering could be. And especially like spearheading, because it's not a massive. You receive a call, you were like, okay, who would want to spend so much time just to fool me? They may. Viruses is a very common form of a host of malware, and for a long time we tell students, oh, you have to differentiate a virus with worm, and then the one way to tell them apart is that a virus needs a user to click on them in order to propagate. Worms will propagate on its own. But for now, it's no longer that important, but just to be aware that there are malware that require you to double click on the email attachment. And then if you have code that just automatically connected to servers, and that's usually it's called a worm in the traditional sense. They don't need you, a victim, to double click because it will contact the server, and the server is up all the time. And then infect the servers, like the code red worm, which we'll talk about in a minute. Word, Microsoft Word, it's a editing software. It may be infected. What is called is a macros. So macros is just a sequence of commands. Think of this like shorthand of commands as sort of packaged into a Word file, and this may be compromised. And so Word file sometimes, if it's infected, also can be dangerous. One of the most famous old-time virus is a love letter virus, which was circulated around the spring of 2000. And it has a very attractive subject. It's an email virus. Subject with the subject, I love you, and then the attachment is aptly named love letter for you .txt .vbs. VBS is a Windows Visual Basic Language, I think. And the VBS by default was hidden. This extension was hidden by Microsoft OS, and so you only see its text file. Or who would not want to have a love letter? And so, and of course, extremely embarrassing to click on it because the virus will send a copy of itself to everyone in your Windows address book with the victim's email address as a sender address. So I remember when I was at grad school, and then when the professor talked about love letter virus, and they were saying, so and so professor clicked on the attachment. One of the viruses, of course, virus and the worms all want to propagate. They're like parasites. All they want to do is to replicate themselves as much as possible. But then they, on the one hand, they also want to hide itself. And virus would want to live as long as possible, so they insert themselves into host programs. And here at the lower left, you see there's different places for virus to insert itself, maybe at the beginning of the program, so it's just make sure it's get executed, or it's insert itself to at the end or the middle of the program, but make sure that there's some jump command that leads to it. And nowadays, you see the code reuse attack, the exploit would make sure that the malcode gets executed right away. Right? So like the Stack Overflow, once you overflow the buffer, then the inserted code gets executed. Another form of virus injecting itself is called a repackaged app. And this is happening a lot in the mobile environment, where you have a legitimate app, attacker disassembling it, inject malicious payload, and then repackage it into something else. It's sort of like a Trojan that we've seen, right? So you have the good component, you also have the bad component. It's called a repackaged app. I have done some work on repackaged malware detection. And it's really difficult to detect it because it has some benign code. And so if you're trying to look for how pervasive certain signature is, certain type of permission, like Android permission is used, or how it's used, or how often it's used, it's not very obvious, because the benign part would dilute the malicious behavior. So we find out that repackaged app usually have this consistency issue, right? So it has some malicious code that gets injected, some random things, and then it has the original part, and then there's some disjoint existing, disconnect between the old part and then the new part, the good part and then the bad part. And so maybe we don't have to analyze the thing as a whole in its entirety. We can break it apart first. We can say, okay, let's see what are the connected components. And then you maybe have one blob that's connected with each other and then another blob, but then they don't have much connection between themselves. And then we analyze them separately. If you find out one of them is bad or any of them is bad, then you say it's very likely this is repackaged app. So that's essentially how we do it. We have this partitioning mechanism. It's just an approximation. We just look at the connectivity in the form of function calls, method calls. If you have a class that calls another class, methods in another class, and then it's connected. And then if you have some class that does not do things, does not interact with other classes, then we say this is a separate blob. And then we analyze each blob separately and give it a risk score. And so here is a concrete example. We look at this family of malware called Droid Kung Fu, which has a lot of them are repackaged. And then we have different features. We see, okay, how frequently they use certain permission, a sensitive permission, high privilege permission. And in this particular app, we partition into two regions called the D region. And we find that they just behave very differently. Okay, and the second region particularly acts as a whole bunch of sensitive permission Android functions, and then we have a heuristic. We have a sort of a policy that would look at the frequency, the type of permission, and then decide is it malicious. And so it turns out our prediction is correct. And then if you do everything together, then you won't be able to tell. So this is this is one work, and we also have done a lot of other similar app detection works, and they all follow the similar type of workflow. You profile the behavior of a program. And so what does it mean, profile? You look at type of calls, type of methods, and then you have some basic idea of maybe the certain sequence of calls maybe malicious. And then it's just an approximation. You never know for sure, right? So but then it'll be bad not to do anything. So you want to have some sort of understanding of what this code does, and then you make a decision. And then of course. Needless to say, the decision could be wrong, and but then because we have seen again and again, malware can evade and it can change, and can tweak itself. But then this is how the sort of the best effort security approach. And this is a point I want to say. Learn a little bit about malware and machine learning, ML, and AI. Even though this is a security course, it doesn't mean that you don't you shun yourself away from ML. Numerous security solutions use machine learning as a detection, especially software classification, malware classification, and you use ML to train existing samples, the known samples, the apps with known labels, malicious and benign. And then you use it to train the machine learning model to classify unknown samples. So it's extremely powerful. And so I encourage all of you to think about how to integrate machine learning elements into your class project. And the machine learning is such a big thing. I mean, it has been big all the time. It's so useful. When I was in grad school, like around 2005, the funny thing is that machine learning PhD graduates need to do a postdoc in order to find a job. And then fast forward to 10 years later, people cannot hold on to machine learning people. They're just such hot commodities. But you know, with data, with this massive amount of computing capability, learn a little bit, you know, learn what TensorFlow is, how to use it. Before we recommend the Weka, you can still use Weka. The neural networks usually use TensorFlow. You can run them on your laptop as well, you know, smaller data set. So I do encourage you to keep up with those modern technologies, and just to make yourself more knowledgeable and more desirable when you're going to job market. And you don't have to say, okay, only ML is, only project with ML is good. No, I'm not saying that. But then if involving ML makes sense, don't be afraid. Virus, this is a very simple slide. Now to highlight just two rows. Rootkit would usually conceal itself, right? So it intercepts system calls and deletes itself. And so they will be able to do it. There's certain type of malware. Will be able to do it. And then malware would also try to remain in memory. So it's not gets deleted, and they can modify address table to make sure it's stay in memory. And of course, a lot of these operations require root privilege. If you hijacked a high privilege server program, then you're all set. So it's very important for system admins. It's very important to avoid running processes with extremely high privileges. And so, for example, if you have an email server, and so it may not be necessary for you to run the server code in the highest privilege, right? So like you create an email admin account and then give the account whatever read write access it needs to function, and then that'll be sufficient. You know, of course it's a lot convenient to say, okay, you have root, then you will not complain. Otherwise, if I don't give you enough privilege, you know, things will throw exception, I got complaints. But avoid giving everybody root. Okay, give them very special accounts so that they get things done, but then they don't get out of their boundary. We talked about virus and we said worm. Last time we looked at how code red worm propagates itself, and a little bit more information. The Windows IS, at least 10, 20 years ago, was extremely popular, just next to Apache. At that time, during the infection, the code red worm outbreak, 1 out of 8 were infected, and that's a lot. But for overflow was involved, and it's in a link library. And then here you see that the worm would fork 300 to 600 threads, okay? And then tried 1 to 2 days to connect to other machines. So extremely aggressive. And if you have a server that does this, it's gonna be bad. The server would be so consumed with this propagation task, won't be able to do anything else, and because this is just taking over a lot of the resources, allocated for benign users, and so certainly extremely bad in terms of availability, right? So when we talk about CIA, and then we say for servers, availability is a big thing, and also let alone it also defaces the server. Rootkit is usually have a root privilege. So operate as a root and try to hide itself. And so when we say Android apps, it's usually operated in the user mode, right? So but then the rootkit has the kernel operating usually in the kernel with a high privilege. And the interesting thing is that one of the most famous rootkit is by Sony. On the music CDs, and for whatever reason, Sony thought that having some special program maintaining digital rights management, preventing users from illegally copying music would be a good idea. Okay, so 22 million CDs has this special code. And the code it does is it's install itself from the music CD. Okay, so you know, and this is of course not all of you are familiar. There's this compact disc, like this big round shape, and then you insert into a CD player, right? The previous workstations, the computer laptops has this cool button. When you push it, something ejected, and then there's this holder thing. You put this in, you put the CD in, and then there's this loud buzzing sound, boom, and then that means it's working, and then you're like, okay, this is great, and you can listen to music and then watch movies. But then for Sony CD, it also install something on your computer, and this program blocks the display of a certain type of files that begin with this dollar sign. And so it's not very good. You cannot just install things on people, so computer, and also you hide files. What if this is hijacked by attackers, right? So the attackers will be able to use this mechanism to hide their files. So as long as you name a file that begin with $SYS, then Sony rootkit will hide them from the users. So a typical way of detecting rootkit is called compare view approach. And first of all, rootkit is not very common because you do have to have the root access. And also, but then it's extremely hard to detect because it's deeply embedded. And one approach, which still this approach is hard to implement, is to compare a higher view of the system with a lower view. And hopefully the lower view is below the rootkit. And so say, the user level, you see 4 files, and then at a lower level, you see 5 files. And then it's because the rootkit hides itself. And so oh, there's some discrepancy that let me investigate, could be a rootkit. And so this is usually how it's like high level approach, but then implementation is difficult because how low can you be? If they already have, the rootkit already has a root privilege, I mean, if you use like system call, and you cannot use ls, right? The Linux command says list all the files, ls, but then the ls is too high of a level, and the rootkit may be already deleting its entry before you see the ls input, the output, right? So you have to actually go below ls. And so I have seen work that go just directly to file systems, like the very basic 0 and 1 bits on hard disks and then reconstruct the file system. You basically rewrite an operating system on your own, essentially, which is just very painful. And I want to talk a little bit about several other types of software attacks. One is, there's interface illusion. When you see a padlock on a browser, do you know is it means the certification is valid or it's just an image of padlock, right? Timing attack, side channel attack, we'll not talk about this, but then essentially when you compute, if the implementation is not very careful, you may have the situation bit one in the key versus bit 0 would take a different timing. This will allow attackers who assumed to be able to observe computation time be able to infer is it 1 or 0. And sometimes it's related to things gets cached and so on. In Covert channel, we'll also say a little bit about Covert channel, but then an interesting quote from Jonathan Millen. At the time when he was invited to give a keynote about Covert channel, he said, "Covert channels emerged in mystery and departed in confusion." And so this just shows how difficult it is to detect Covert channel. But go back to trusted display. So let's consider a certain scenario. User need to enter credit cards into a browser. And then every time I make online purchase, I'm afraid that my browser is already compromised. What to do? And so that's a problem. The threat model is you have a browser could be compromised, OS could be compromised as well. The server is trusted. The Amazon.com server is trusted. You can use special hardware, okay? So the hardware is generally trusted. And then the goal is, of course, for the user to enter credit cards in a secure way. So how can this be done? And then for almost all the questions that involve OS being compromised, you just have to have some special hardware because something needs to be secure. Okay, you need to have a root of trust. And most of the time, OS is assumed to be trusted, to provide root of trust. And if you say, okay, OS no good, then you have to have some special hardware that will be able to do some computation for you. So one of the approach that I'm going to talk a little bit about is have some sort of encryption. You involve special hardware and then make the hardware do work so that all the secret information, whenever it's flowing through OS, flowing to browser, flowing to certain components that you don't trust, it stay encrypted. It's only when the information reach the trusted entity, it can be decrypted. So that's it. So that's really the basic approach. That is the only way to solve the problem where you have this massively insecure system, right? Browser, OS, massive, everything is insecure. And then you just tunneling through them, okay? And of course, the assumption is that malware residing in OS, residing in the browser as a plugin or whatever will not be able to decrypt. Okay, and will not have the access to the decryption key. Only the trusted devices have the decryption key. So think a little bit, a few seconds, how would you do it? How would you implement this? Who would have the decryption key? who would have the decryption key? So, and this is a solution, and there's a lot of solution that following this type of flavor. This particular solution comes from a group from Stanford. And so the trusted devices that have are given the key are the keyboard and the monitor. Okay, so when user enter credit card numbers into the keyboard, then the credit card numbers are immediately encrypted. And then of course the typical keyboards would not be able to do encryption, right? So I'm holding up my keyboards here. In this device cannot do encryption, and so they use a Raspberry Pi attached to it. And so whenever, and of course assume the keyboard is not infected. And so all the bits going to the Raspberry Pi, which is here, will get encrypted, and then you're just tunneling it to the operating system, and you don't care OS is bad or not, because the credit card numbers is encrypted. And then it uses this special hardware called the Intel SGX. It creates a component in your system enabled with hardware called Enclave. Enclave is just some blob that is able to do secure computation, storage, and then it's just so secure. It's very secure blob, bulletproof. You almost can say that no one will be able to take it apart. Okay, and then the enclave will be able to encrypt the credit cards directly into the display, and then be able to the display will be able to decrypt it. And then we assume the monitor is trusted. And of course, the monitor cannot do the typical monitor cannot do decryption, and therefore there's also another Raspberry Pi that does this for the monitor, right? So essentially everywhere you go, things are decrypted, and whenever it's things are encrypted, and only it reach the trusted entities, things get decrypted. Okay, so that's essentially the idea, and of course the whole enabler is this enclave. Without enclave, you can encrypt things, but then no one can decrypt it, and then if the things get decrypted, they will immediately get hacked. And so with enclave, we assume that enclave cannot be hacked. And the keyboard to enclave communication is encrypted, and the monitor to enclave, the enclave to server is all encrypted. And so you're just tunneling back and forth. Okay. And the enclave is an enabler that enabler for this tunneling mechanism. So that's how you achieve the trusted display and protect your credit cards. And of course, it really requires special equipment, because it is a strong assumption. The OS is compromised, browser is compromised, strong assumption. And then, by the way, they have a very cool demo, a very short demo as well. And so the user will be able to see this type of typical interface, and this is taken by a photography by phone. I mean a camera, right? So, but then the malware won't be able to see it, because the malware, if the malware tries to do screen capture, they won't be able to decrypt anything. Only the trusted display can decrypt. So trusted display always need special hardware, and special hardware requires special instructions. And this is just you cannot have security out of thin air. It's security depends on root of trust. Intel SGX is extremely popular. It stands for software guard extensions. It provides memory isolation, encryption, storage, and so many applications based on SGX. And it's not the first hardware security component many years ago, like 20 years ago. Yes. TPM, and it's called, stands for Trusted Platform Module. IBM was one of the earliest designer, developer, adopters of TPM, provides secure computation and a secure storage, and you can do encryption, decryption, signing, random number generators, and also relatively cheap. Like somewhere I read $8 a piece, and that was a while ago. And a lot of at that time, a lot of the laptops actually came with TPM pre-installed, and then you have to enable it. And of course, all of these hardware-enabled security solutions assume hardware is secure. And of course, hardware sometimes may not secure, may not be. It can be problematic in some rare occasions. But this still would be providing stronger security guarantees than solutions without hardware security. And sometimes it's you do pay a performance overhead, because when the system switch to the secure mode, it takes time, right? So for example, you have the regular memory, and then you have this special SGX memory, and then there's a switch, and then the switch, context switch takes time. There's overhead and back and forth, and there's always slowdown. I want to say a little bit about Covert channel, and this is of course not very intuitive. Covert channel, it's very subtle. It's very subtle, and so the concept is you have two attackers, one inside of an organization, one outside. Okay, so the inside, malicious insiders, has certain privilege, will be able to access some data, and then would stealthily leak the secrets to the outside attacker. Okay, so think of this way: instead of calling the attacker friend outside saying, hey, by the way, today's PIN for this bank transaction is 1234. Well, that would be too obvious. So people would say, oh, you're a bad agent. And so no, the insider would do it very secretly. The insider will try to say, put up the mail. Okay, and then with maybe set up the mail flag to indicate a 1, and then put down the flag to indicate the 0, and then the outsider will just drive past the insider's home and just look at the mailbox configuration. Is a flag up or down to figure out the PIN. Okay, and then in the whole time, no one will be able to realize that they are actually communicating, but they are just covertly. And so this is another example, file lock covert channel. So you have this is the outside. This is let me see. Okay, the lock. Well, so oh yeah, you have the insider will be able to control the lock. Okay, control the lock of a file. Okay, so the insider will be able to send out signal whether some file is locked or not, 0 or 1, and it depends on some secret data. Say the PIN or so on. Okay, And then the PN, the spy, this is the outside attacker, would not be able to directly observe the PN, okay? But then be able to observe whether a file is locked, okay? And you may ask, what does it mean for a file to be locked? And just to think whether a file can be writable or not, so something like that. And then the spy will be able to infer the value of the secret data. Okay, and so then you can think of this in many different ways. Again, very subtle, very confusing. Almost you never know whether this has been used in reality. Okay, because there's no way for you to detect this, because you have to correlate with some secret. That means it's just too difficult. A closely related attack, it's a stealthy information sharing mechanism called steganography. Steganography is to hide information under a cover, and it could be image, it could be a file. Image is very common, and so this is I use some Windows steganography program to make this, the cat image actually is embedded in this tree, so you cannot tell, right? It's actually, there's a cat image, and after extracted, then you see a cat. And then I stopped having Windows machines, and so no longer keep track of this. But the idea, one of the simplest ideas, quite effective, was invented in the early 90s. You just replace some least significant bits in image, in each pixel of the image. So you have a whole bunch of pixels, and then for each pixel, it's just an array. And then the most significant bits you don't touch, because those are very important. And then sometimes they have like 256 bits. The least significant bits, so almost nobody cares, because it doesn't really matter what it is, 1 or is it 0. And then you just embed the most significant bits of your hidden image into those and into the end. And then be able to, as long as you agree, and then sometimes just two bits per pixel would be sufficient. You just embedded the 2 most significant bits of your secret image into the 2 least significant bits of the cover image. And the reason that this is still okay, because human eyes are very good at inferring information, and can have a high tolerance of inaccuracy. So I want to just say that this is an article that talks about the use of steganography in the wild, and it turns out some spies, and this was 10 years ago, used steganography, and this is some of the agents from Russia actually use steganography to communicate. Before we end today, I want to just say a little bit more about Fred Cohen's paper. In the paper, we have talked a little again and again about the impossibility theorem, but it has a lot more information. And interestingly, he also said that USC, where he got his PhD, told him everything he needs to know all the way down to the bottom. So it's a very, very nice compliments for his alma mater. The undecidability, and this is again is the proof where he proof by contradiction, where he showed that the virus would always be able to change its behavior, and then contradicts what antivirus program decides. And so, but then he also, based on that, have drawn several other conclusions, undecidable problems also include the detection of a virus by appearance or by its behavior, understanding the evolution of virus, whether this and that are related in the same family, understanding the triggering mechanism, are all impossible and undecidable. Interestingly, he also mentioned that the detection of a virus detector is undecidable. That is, if I want to know, am I executing in a honeypot environment? Am I being scanned by a virus detector and the antivirus system? It's also undecidable. And so why is this? What's going on here? And so it turns out a lot of the attackers, and they don't want to attack just about anything. They only want to attack when they're in a real environments. If they sense that they are in a honeypot environment, then they will choose to do nothing, because because they don't want defenders to observe their behaviors, right? So that becomes relevant. So a virus would want to figure out whether or not it is being executed in a honeypot environment, being monitored by the virus detector, and that's undecidable. So that's good for defenders, bad for attackers. And so everyone can adapt. Anyone can have adaptive behaviors. It just the undecidability says. So then it's the paper talked a little bit about how to solve the problem of virus spreading. What is the brutal brute force way of preventing virus from spreading? The quick and dirty way. Well, so isolation, right? So you just unplug the power outlet, unplug the internet, turn off your Wi-Fi receiver. No information sharing, no internet, and no virus propagation. But then how realistic is this in practice? Pretty much useless, right? So if you have something like that, well, why don't you recommend everyone go into the Stone Age? It's the humanity is progressing. There's almost no way people will go back, just for security, and also it will be very boring life, and so it's just not very feasible. Then how about so just as a mental exercise, the paper back in the 80s talk about this partition model. Maybe there's some ways that we can partition the files, the users, into groups, so that you can have like high risk people and low risk people, and then you're like, okay, if you're a military general, and a lot of this discussion is in the government and military space, general, or like operate with a high integrity, high access level, and so you put them all together, and then they can email each other, share files, but then you don't want them to share files and with low integrity, low access group, which underlying assumption is that we'll probably have more opportunity to access high risk content. So that partition model is also equally strict, and we're gonna have some more discussion in that next class. It's called the BIBA model, and there's also Bell-Abdullah model. There's a very popular 80s models, and then you will see it's not very feasible. But then at that time, the control information weighs a lot more than flexibility, and so at that time it was actually quite popular, and there are systems that implement this. You just have a different, given a user, you give it a different class. Okay. Another model is called the flow model that was described by Fred Cohen. No partition, but then it depends on the path where you receive this information. And so the information receiver would say, oh, if this path goes through some really bad entities, bad users, or untrustworthy or unknown users, then I don't accept this. I throw this to the trash. And suppose that you have like 4 people, you can send information to each other. And then they have their different policies. A will say, oh, I only trust what B sends me. Okay, if B sends me an email, I feel comfortable opening the attachment. And D would say, I only trust what A says, and so, but you know, like if A directly tell me something, I would accept. But then if A tell B and then B tells me this, so like a chain that's passed through B, A, B, D, then I will also accept it because I also trust B. But then in some cases, A would tell C, and then C say to me, hey, you know, this is a file that A asked me to send you. I don't trust it because C may embed, you know, some malware, repackage it. I don't trust it. I don't want to open C because I don't know C very well. So this is a flow model, which is very interesting, right? So you can already see it's complicated to maintain. And so suppose one day C's machine gets infected. If you have a model like this, a flow model like this, then you don't have to worry because D will not trust C, right? So D may receive some virus propagation file from C, and then D will just drop it, will delete it. So the virus will not propagate it to D because D had this prior policy. And of course, this is very arbitrary, right? So, you know, how do you know who is trustworthy? You know, like, so maybe B is not as trustworthy as D would like him or her to be. And so if B gets infected, then D will get infected as well. And a lot of this leads to back in the 80s, there's the access control models. It's defined by user. Okay, so and so this is a flow model, and of course none of this is being used right now. But you can sort of envision some kind of a file system access in that kind of flavor. It will be a little hard to manage. The typical Unix, Linux file system based on Unix is the owner of the file would specify who gets access, and usually based on groups. And so if you are in a certain group, you'll be able to access a group role. And so I want to wrap up just with this slide. We spent a little bit of time talking about program analysis, and including CFI, right? That control flow integrity would involve using static program analysis to model the behavior of the programs. And so there just has been around, those techniques been around for several decades, extremely useful for security. I encourage some of you to use these techniques in your class project. And of course, this is approximation. It's very important to know that nothing is absolutely accurate, but you do want to have be as accurate as possible because there are training data set with known labels. You can validate, am I doing it correctly most of the time? And of course, detecting zero-day malware is still very difficult because a lot of this analysis is based on past samples, the previous samples. If you see a completely new attack patterns, it's going to be very difficult. Staying ahead of attackers is what defenders need to be. It's going to be a constant struggle, a constant mouse and cat game, arms race. And so you understanding how attackers think is very important. That's why we do this Stack Overflow attacks, and we keep talking about defense in the context of attacks is very important. All right, that's it for today. Next class, we want to say more about OS security. I also want to talk about authentication, authentication of users, authentication of files and things. That's it. Have a nice weekend. Bye.